I remember all of those rectifiers were based on charging a capacitor and then loading it with a resistor. So basically, each of the output waveforms of that capacitor look one way or the other, just like the one we've looked at in this figure here. Full wave rectifiers would also draw current from the grid during the negative half cycle, not just during the positive one as we've seen here in the half wave rectifier, but basically the capacitor voltage would rise and fall, and it would depend on the load of the resistance here, the resistor, and it would depend on the size of the capacitor, and otherwise there is nothing you can do about it. Now, as loads are varying, and sometimes they can be in idle, then they wouldn't draw any current, then the voltage would be rather high here, would be always across close to the top, the peak voltage of the AC mains across the capacitor then. Or the load might have a spike, like having a processor there, a microprocessor or a graphics processor. The load might vary extremely much, having, for example, a graphics processor. When the display is changing and the picture is moving, then you would have a whole lot of processation here and draw a whole lot of current. And when the picture is frozen, for example, you press the pause button when you're watching your Netflix, then all of a sudden the voltage would rise to the highest voltage that it has after potential transformer there. And these voltage differences occurring there would not be good across the load. So you actually add typically another stage, and the most simple one you can add is a linear regulator. Now, whether that IC would be good enough to provide the energy for a graphics processor or not, I doubt it. But it's a very classic one. The LM7805 is a old school style IC, a linear regulator that provides 5 volts. That's coded here in the number 5. So there is also an LM7810 that provides 10 volts then, or a 7807 providing 7 volts. And then there is a 7905 which provides minus 5 volts. Now that IC also provides about 1 ampere at the output here. What it does here now compared to not having it, it's contributing here with that Zener diode down here, which has a stable voltage. So assuming again our load is something that draws a lot of current and then stops drawing current, that would change the voltage across the capacitor at the output. The basic operation first. So we have that kind of varying capacitor voltage at the input here, the ones we've looked at. So it looked approximately like that. Rising, 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 and then discharging, discharging, discharging for a long time. And then one of the diodes is conducting again and it's discharging here. The y-axis here is the voltage across the capacitor, in this case the input capacitor, and the x-axis here is the time. So that's the voltage across that input capacitor here. Now this Zener diode comes into play. The Zener diode is generating a very stable voltage reference here. So assuming we want 5 volts at the output and knowing that we have a bipolar transistor up here, this one down here could be, for example, a 5.7 volt Zener diode. So if we got 5.7 volts here, then we would have a voltage drop across the base emitter of the main power transistor here of roughly 0.7 volts. That's intrinsic in a bipolar transistor, 0.7 volts here, and that gives us at the output approximately 5 volts here. If we look at Kirchhoff's voltage law following that loop here, ending up with the exact 5 volts that we want both across the output capacitor and across the load. So now what happens here if the load is increasing, meaning the load resistance is actually dropping, we are drawing more current from the output of that linear regulator. So that blue current up here would increase. The capacitor here would discharge over into the resistor here, following that current pass here and going back here, going back through the capacitor. Voltage would drop across that resistor. That means the base emitter voltage across our transistor up here would rise. The voltage on this node here, on that node, is dropping, so we're actually getting more voltage, and that's because this voltage is rock steady. That one would always be 5.7 volts. If that base emitter voltage is actually rising here, that means the collector emitter voltage, this one here, would also be rising. That's the characteristics of a bipolar transistor. And that means the capacitor is getting charged with more current, and there is also more current provided to the load through the linear regulator, and the output voltage is regulated to be stable again, is rock solid at 5 volts. This blue event here would be called a load regulation here. So the load is changing, and we've been looking at it now if the load is actually requiring more current, and it's vice versa if the load would require less current here. Now let's have a look at another scenario, keeping the output voltage and the load stable, always drawing the same amount of current from the power supply, but now taking into account that the input voltage is actually varying, like we've assumed here all the time, that this is the capacitor voltage around here. So with the rising capacitor voltage, this one here being bigger, means that the voltage across the transistor and the load would be rising. So that's that loop here. And with the voltage across the transistor rising here through its transistor equations, also the collector current of that transistor would be rising. The collector current rising means that the capacitor is getting charged more, and that would lead to the voltage from the base to the emitter to actually drop. Dropping voltage across the base emitter would mean that the collector current, this one here, is going to be dropping again. And when this one is dropping for the higher applied voltage, for example, if we are approaching the maximum of the input voltage here, we would transfer less energy to the output capacitor. And in any case, the voltage at the output would stay stable, rock steady at 5.0 volts. That's exactly what we desire. So now it's your time to actually apply some numbers to such an example. The linear regulator now packaged into a 3-terminal device. That's how you typically draw it in schematics here. Having an input voltage, an output voltage, and a connection to ground. The capacitors are not drawn in this case here. I've just left them out for simplicity reasons. And you're supposed to figure out what the maximum efficiency of that linear regulator can be for those given quantities.